Hi there, welcome to this video where we're going to continue taking a look at the contents of Whitehead and Russell's Principia Mathematica. So in particular we're looking at the first edition and mostly volume 1 in this video, although there are a couple of things from volume 2 that I'm going to be briefly mentioning. So this video follows on from the previous video that I made where I didn't get through quite as much as I anticipated. But like that video, in this video, we're going to be looking at things a bit more informally. The video's not very well scripted. I've got a few notes surrounding me to try to give me a bit of an idea about the kind of things that I want to talk about. But it's very likely that I'm going to go off script in this video. So the fact of the matter is either these videos are going to be useful to you or they're not. If you don't like them, don't watch them. But maybe there's something useful in there. The only way to find out, though, is potentially just to watch the video. So I make this content, I make it freely available. Whether it's useful, that's an entirely different question. I hope it is, but you might just have to do a little bit of work. You might have to be a little bit patient to find the stuff that's interesting and useful to you. So if you bear with me a second. Okay, so I'm going to start off this video just by looking at another proposition. It's one that I wanted to cover in the previous video, but I thought that video had already gone on long enough. So we're going to take a look at another proposition. It's proposition 62.34 initially. And then there's some kind of conceptual stuff that I want to talk about relating to Principia Mathematica for probably quite a large part of the video. We're going to be talking about cardinal numbers and similarity of classes and things like this, but in a purely informal way. Okay, so I'm not going to be going through systematically the contents of Principia Mathematica, and this is what I mean when I say it might just be a little bit of work for you to find the stuff that's actually useful and interesting for you. But let's start with this proposition, 62.34. So this proposition states that P sub epsilon is, I forgot my dot, is equal to the sagitta of P, the relative product of the relations P and epsilon. Okay, so I liked this proposition for several reasons. One is it incorporates so many different relations, particularly a lot of the relations that were introduced in chapter 37, where it can get quite confusing. At first, it can feel quite confusing with all of the different relations that are introduced. So I'm not interested in the formal demonstration, if it can be called such a thing, that Whitehead and Russell give in Principia Mathematica. The whole point of this is that I'm personally starting to try to build a picture in my mind about what this proposition represents, how I'm going to visualize it, how the parts fit together, why I feel that it should make sense, maybe give me some insight into how I might start to prove it. But I'm not here to actually prove this proposition. That's not what I'm trying to show here. I'm just wanting to give some kind of insight into how I process the information, potentially in certain contexts, the information in Principia Mathematica. I'm not saying what I do here is the way to go about things or it's the best way, anything like that. All I'm saying is that this is how I potentially might go about thinking about this. And hopefully it'll give you some, ideas about how you might be able to incorporate some of these ideas, if you need to, into your own analysis of Principia Mathematica. So either you find, like I said, either you find it useful or you don't. Okay, so as I'm looking at this, I can see there's various concepts all over the place that I know that I'm going to have to unpick. So one is this relation P sub epsilon. I can also see that I've got a relative product of two relations that I'm going to have to figure out. I'm going to have to remind myself what this sagitta relation is. I can see that I've got a descriptive function involved, which tells me that there is going to be a unique object corresponding to this symbol, this sagitta primed of the relative product of P and epsilon. I know that epsilon it's a fixed relation within Principia Mathematica, whereas P is it's more of a generic proposition. Generic relation. And P sub epsilon it's a relation that has some kind of connection with P. And it would also appear that this P sub epsilon also has some kind of connection with this relation epsilon. And this is another reason why I particularly like this proposition, is because it highlights something that it indicates to me something that wasn't evident when I first read chapter 37. Why the notation? So if you've seen chapter 37, you'll see the notation R sub epsilon, which we'll talk about in a second what that represents. And for a while, I kind of had a bit of an idea about why this notation might be chosen, but this particular proposition really indicated to me what might have motivated that particular notation, that choice of notation, R sub epsilon. I don't know for definite. It's all speculation. And this is one of the things that I love about Principia Mathematica, is that some people might find this frustrating, and it is frustrating, that sometimes you don't know things for definite. I don't know for definite how Whitehead and Russell were viewing Principia Mathematica, why they decided to represent such and such a concept in this particular way. Maybe there are answers to these questions, and maybe there are answers to these questions that are buried in some books or articles somewhere that I haven't read yet. But maybe those answers are things that you can only really infer the possibility from such as this proposition here, for example. And I like doing that. I like doing that sort of that sort of digging. It can be quite frustrating in that you don't know for definite. But anyway, so what is this P sub epsilon? Okay, so you're going to have to bear with me with this, by the way, because I've got a couple of notes here, but I'm going to be doing this pretty much live, so I might have to think for a little while from time to time. So just bear with me with this one. So P sub epsilon, this is... so when does this relation hold? So X P sub epsilon Y holds... And I might have to modify this notation. Initially, when I'm figuring out what things represent, I'll be quite generic with my notation. So here, X and Y, I don't know yet whether they're going to be classes, whether they're going to be individuals, whether they're going to be other relations. I'm just using X and Y initially. And if I need to, I will go back and I will kind of rewrite. Let's say I figure out that X is a particular type of object. Maybe it's a class. Then I will maybe go back at some point and I'll change the notation to something that's more indicative of that particular object being a class rather than, potentially an individual or something like that. So maybe alpha. Alpha is used in Principia Mathematica very often to represent a class. So maybe I'll change it as I go along. But I'm just using kind of generic terms here. So X P sub epsilon Y holds whenever X is equal to P double primed Y. Okay, so what is P double primed Y? Well, okay, I'm already starting to get the feeling that I am going to need to change. X is actually going to be a class here. P double primed Y is going to be a class. So this notation, this double primed here, indicates to me that X is going to be equal to a class. But we'll okay, let's do that then. Let's change X to alpha. Okay, So P double primed Y, what is this? This is the class of terms. I can use X now. Class of terms X, such that X, P, Y holds for some. Aha, okay, so Z in Y. So again, Y is actually a class here. So I'm going to change the notation again. So I better do it. I better be careful. So 1, 2, 3, 4 places. I need to keep track of them somehow. So beta, 3, 4. Okay. Right. Okay. So, and this is how it works for me. I'm gradually building a picture of what's going on. So alpha, P sub epsilon beta holds whenever alpha is equal to P double primed beta. P double primed beta is the class of terms X such that X, P, Y holds for some, it should have actually been Z there, made a mistake. Such that X, P, Z holds for some Z in beta. Okay, so in other words, I know that there is a unique alpha that that does this job, that is equal to P double primed beta. So in other words, P primed epsilon, this may or may not be useful, by the way. Beta is equal to P double primed beta, and I can also write therefore that P double primed beta has relation P sub epsilon to beta. So in other words, P sub epsilon is the relation of the class P double primed beta to beta. Okay. So that at this point, I'm feeling quite comfortable with what this thing represents, this P sub epsilon. Okay. It's the relation of the class of terms X such that X, P, Z holds for some Z in beta. It's the relation of that object to beta. Right, so now let's move on to this sagitta thing. Sagitta primed P epsilon. So there's a few things that I'm going to have to look at here. One is this sagitta. Another is the relative product of P and epsilon. I'm going to have to figure out what epsilon is, potentially. P is just a generic relation. But also I'm going to have to satisfy myself that there is actually a unique, potentially a unique object that is the sagitta of the relative product of P and epsilon, because here we've got the dash here, so we've got a descriptive function here, right? So with a descriptive function, there is a unique object that is the referent. I can't remember. I never get them. I can never remember which way around it is. Referent or relator. Let me have a look. 32. I think it's going to be useful. It's a relation of the class. Right, reference on the left. Right, okay, the left-hand side. So, what is sagitta? Sagitta is the relation. This will hold. It's between two. I know that this is between two relations, and it's so if we've got S, SG, R, this will hold whenever S is equal to R right arrow. This is a unique object, and I know that it's because there is only one R right arrow relation. So yeah, I'm happy that there is a single sagitta. So in other words, the sagitta of R is equal to R right arrow. Okay, so what is the relation R right arrow? So I know that R right arrow relates a class to an object. So alpha to Y holds whenever alpha is the class of reference of y with respect to R, with respect to relation R. So what does that mean? It means that alpha is the class of terms x such that x, r, y holds. Okay. So, Sagitta, the Sagitta of P, the relative product of P and epsilon is going to be equal to the relative product of P and epsilon with a right arrow over it. Okay. Right, so I think I'm going to have to go onto another page now. So I need to figure out what this P, the relative product of P epsilon right arrow is going to do. So there's quite a lot to figure out here, and you might think, well, what's the point in going through all of this when you've just got the proof here? The demonstration of this is 3 lines in Principia Mathematica. The point of this is to try to build in your own mind an intuitive feel for what these things represent. It's one thing to treat everything in a purely formal way. There is a time and a place for that, and it does have its uses. But sometimes when you're working on a purely formal level, you can kind of sometimes you're not helping yourself to build an intuitive picture. So it's like trying to do, for example, differentiation without having, basic differentiation without really having that idea in the back of your mind about gradients and tangents and things like that. Now, obviously, that intuitive stuff can actually be a bit of a block beyond a certain point. It can be quite, if you take it too literally, and you're relying on it too much, then yes, it can cause you problems. But to really get a feel for differentiation, for example, it really does help to have, on some level, some kind of picture as to what differentiation is kind of geometrically corresponding to. At least that's how it is for me. Okay, I would struggle to do. I would have struggled to learn differentiation when I first learned about it without that kind of visual aspect to it, treating it in a purely formal way. I'm not saying everybody's like that. That's just how it is for me. Okay, so let's have a look at this P, relative product of P and epsilon. So relative product is in section D, part 1. I don't know which, maybe 33 or 34, maybe 35, something like that. I don't know. So this will hold, what symbols shall I use? Z and W. This will hold whenever, if and only if, there is, not necessarily unique, there is a V such that Z, P, V, and V, element of W, both hold. Right? So, importantly, both of these have to hold. Okay, so, right, this epsilon, by the way, this is the relation of, this is the relation that relates members of a class to the class itself. Right, so this is a fixed relation. So this means exactly what you expect it to mean. V is a member of W. Well, W then must be a class. Okay, so here I can modify my notation again. So let's go for gamma. Okay, so this holds if Z, P, V, and V is a member of gamma hold. Okay, so therefore, epsilon gamma, this is the class of class of terms Z such that ZPV holds and V is a member of gamma hold. Okay, so it's the class of all terms Z such that ZPV holds whenever V is a member of gamma. Okay, so how does that compare with what we had earlier? So, okay, where am I going with this? I've lost my train of thought now. Aha, okay, so yeah. So P epsilon, this is the relation of so this is effectively, if we look at this, ZPV and V is a member of gamma. This is, for all intents and purposes, P double primed gamma. Compare that with what we had before. The class of terms P double prime beta is the class of terms X such that XPZ holds for some Z in beta. Compare that with, it might help if you actually write these out next to each other. It's a shame that I've got to switch between different screens here, but this is the class of terms Z such that ZPV holds when V is a member of gamma. It's exactly the same form. So this is the relation. So P, the relative product of P and epsilon right arrow is the relation of P double prime gamma to gamma. But we've also seen that this is equal to the sagitta of the relative product of P and epsilon. But the relation of P double primed gamma to gamma is exactly the relation P epsilon. The only difference here is that I'm using gamma instead of here where I used beta, which kind of establishes the equality here to a certain extent. I'm not trying to prove things here. I'm just trying to show how I kind of build a picture. So it's taken me a while to do that, but hopefully you kind of follow what I've been trying to do with that. Again, any questions that you want to ask, just feel free to ask them. Okay, so I hope that made sense. No guarantees though. Right, so let's have a look at something else now. What I want to talk about is the cardinal numbers 0, 1, and 2 as they're initially introduced in Principia Mathematica. So in volume 1, we don't get a definition of cardinal number. This has to wait till volume 2. Right at the beginning of volume 2, we get the definition of cardinal number, and there's some difficulties surrounding this, which I'm going to briefly touch on in this video. But there are some difficulties, some potential difficulties surrounding the concepts of 0, 1, and 2 as they're introduced initially in volume 1. So we've got a definition, I've got them, I can't remember the numbers of the definition, 54.02. 54.01, sorry. Yeah, 54.02 is the definition of 2. Okay, so 54.01, this is the definition of 0, the cardinal number 0, which is the unit class of lambda. We've got the definition of 1, which is definition 52.01. 1 is equal to the class of alphas such that there exists an x for which alpha is equal to the unit class of x. That's the definition. I'll talk about 2 in a second. Okay, so one is effectively defined to be the class of all unit classes of a particular type. Okay, so we've always got to be conscious in Principia Mathematica. We've got all of these different things called types. What is a type? A type is effectively a class of objects. Okay, a certain class of objects. And there's, maybe I shouldn't say an infinite number of types, although there are. It's just that we don't have kind of an understanding of finite and infinite and things like that at this stage. So maybe I'll just use a more neutral term like unlimited, something like that. There's an unlimited number of types. No matter how many types have been generated, we can always generate more types. Okay, so we see this from the hierarchy of a functional hierarchy and propositional hierarchy and things like that. That you can always you never have to talk about the hierarchy as a whole, but it is in some ways it's potentially infinite, if not actually infinite. Okay, it's at least potentially. Okay, so one is defined to be the class of all classes, class of all unit classes of a particular type. What are unit classes? Unit classes are classes which have exactly one member. Okay, so notice that 0 is defined as a unit class, the unit class of the null class. In other words, the class whose only member is the null class. So it would seem then that 0 is a member of 1, because 1 is the class of all unit classes of a particular type, and 0 is a unit class. Therefore, 0 must be a member of 1. But this is not the case. So this is where you've kind of got to keep a track of things. You've got to think quite carefully about what's going on. So if we take the 0 and 1 here as corresponding to the same type, then we do not have 0 as a member of 1. Okay, 0 and 1, just like in the previous video, I was talking about lambda being a typically ambiguous symbol. 0 and 1 are also typically ambiguous. So what do I mean by that? So to each type, we've got a null class. Okay, so conceptually, these are very similar. As we move from one type to another, the null class, kind of psychologically, it's the same thing, but logically they're distinct. But they're so similar that we just use the same symbol. Generally speaking, we just use the same symbol, whether we're working with this type or that type. If we want to talk about the null class of this type and we want to talk about the null class of that type, we tend to just use the same symbol, lambda, okay, uppercase lambda. So this is a typically ambiguous symbol. However you view this is entirely up to you. You might view it as some kind of empty abstract form, such that when it's placed in a particular context, then it's almost like it gets filled with. So the class 1, for example, it's a class of classes. There's a 1 that corresponds to each type. It's almost like it's an empty form, empty abstract form, and when it's placed in a particular context and it needs to become of the 1 of that particular type, then it's almost like it's filled with the unit classes of a suitable type to play that role. I mean, that's just a kind of intuitive way to think about it. Not necessarily how you need to think about it, but maybe it's one way to kind of get your head around it a little bit. There are ways that we can kind of distinguish if we've got a null class, 2 null classes in the same context coming up, but they're corresponding to different types. They're not the same thing, right? I pointed this out in the last video. Whereas you've got a unique empty set in a lot of modern axiomatic set theories, in Principia Mathematica, the lambdas, the null classes corresponding to different types, they're not equal. It doesn't even make sense for them to say that they're equal or not equal as such. But they are not equal. They're not the same object. They are distinguishable from one another. And it is possible within Principia Mathematica. There is some notation that I'm going to talk about, I think, later in this video, where we can start to talk about, we can separate, we can distinguish lambdas from different types to a certain extent. If we need to. We don't always need to, though. So if we take 0 and 1 as corresponding to a certain type, a certain fixed type, then it's certainly not the case that 0 is a member of 1. And why is that? Okay, so if 0 and 1 are of the same type, they are classes of the same type. So their classes are determined, the type of a class is determined by the type of its membership, the type of its members. Two classes of the same type must have members of the same type. Okay? If a class has members of a particular type, the class is always one above, of a type one above that of its members. So this is very different to one of the difficulties that we had with propositions and the functional hierarchy, is that a function is not completely determined. The type of a function is not completely determined by the type of its arguments. We saw this. I've explained this in a different video, but with classes it's a different situation. So of course the null class has no members, but it's still, there is a way to deal with this, to talk about the type of the null class even though it doesn't have members. And that's, we don't necessarily define the type of a class purely in terms of the type of its membership, because that fails with the null class. There's ways to deal with that, so that to each type we do have a corresponding null class. Okay, and there's an infinite number of them. So the membership of the class 0, well, it's only got one member, which is the null class, lambda. Let me get rid of that one over there. In the class 1, its members are of the form iota primed x. Okay, so these must be of the same type. If 0 and 1 are of the same type, then lambda and iota primed x must be of the same type. Okay, so, but lambda is not a unit class, right? Lambda is a class with no members. So 0 is defined to be the unit class of lambda. So this must be of a different type to lambda. So iota primed lambda must be of a different type to lambda. So iota primed lambda and iota primed x, these must be of different types. So there's no contradiction here. When we say that 1 is the class of all classes, a class of all unit classes of a particular type, on the one hand, and on the other hand we're saying that 0 is a unit class, but it's not a member of the class 1. There's no contradiction here, because 0 is a unit class, but of a different type to the unit classes that are contained in, that form the membership of the class 1. Okay, so this was just to kind of clarify that little point. I thought it was something that was could be a little bit confusing. But then I'm going to move on to the cardinal number 2. So this is definition 54.02. The cardinal number 2, and there are different versions of different 2's that are defined in Principia Mathematica. So there's the cardinal number 2, there's the ordinal number 2, and then there's this other one that we came across in the last video, which is 2 dot, which is, it's not the cardinal number 2, it's not the ordinal number 2, it's something, it has a relation, particularly to the ordinal number 2. It has a particular relation to the ordinal number 2, but it's not 2. It's not either a cardinal number or an ordinal number. It's just a class of objects that has a particular relation to the cardinal number 2. Okay, so 2, the cardinal number, is defined to be the class of alphas, such that there is an x and a y, and x is not equal to y, and alpha is equal to the logical sum of the unit class of x and the unit class of y. So, okay, for reasons of significance here, it does require that x and y are of the same type. And therefore, the unit classes iota primed x and iota primed y must be of the same type for this logical sum to be significant. So naturally, if x is not equal to y, if we've got a class who's only with exactly one member, another class with exactly one member, and they're not equal, put them together, you get a class with exactly two members, two distinct. 1 plus 1 equals 2, would you believe? So it kind of makes sense to define the cardinal number 2 in this way. Now, what is the problem here? Well, the problem is that in Principia Mathematica, in the system of Principia Mathematica, it's not possible to prove that there is more than one individual. Principia Mathematica can only prove that there is at least one individual. It doesn't say that there is exactly one. It doesn't deny that there might be more than one. It just says that there is at least one, and we cannot prove that there is at least two individuals. So this is a consequence of one of the propositions in section C of part 1, which says something like the null class is not equal to the universal. No, I don't need that, do I? The universal class in any given type. So classes are determined entirely by their membership or lack thereof. So if we've got two classes which correspond to a particular type, and neither of them have any members, then they must be both equal to the null class. So any class that has a member cannot be equal to the null class. Okay, so therefore, if the universal class is not equal to the null class, then the universal class must have at least one member. But again, we cannot prove that there is more than one. That it has more than one member if it's the class of individuals that we're talking about. Once we go higher up, things change a little bit, but when we're on the level of individuals, we cannot prove that there is more than one. So what that means is that there may not be an x and a y such that x is not equal to y. In which case, so if we take worst case scenario and there is only one individual, so assume we've got exactly one individual, then if we can't talk about two in that type, the type that corresponds to individuals, the class 2 will be equal to the null class. And when I say that 2 will be equal to the null class, I don't mean that 2 will be equal to 0. I mean that 2 it's a class without any members. 0 is a class it has a member. It's a unit class. It's a class with a member. It just happens to be that member is the null class. But 2 would just be equal to the null class. 3 would be equal to the null class. 4, 5, 6, 7, whatever. As soon as we get past 1, all of the cardinal numbers beyond that will be equal to the null class. Now, it might be that there are indeed more than one individual. There might be 2, there might be 3, there might be an infinite number. We don't know. So this might not be the case, but this is worst case scenario. Now, if we assume that, again, there's a finite number of individuals, then once cardinal numbers and order and things like this have been defined, then what we'll find is that after a certain cardinal number, all of the cardinal numbers beyond that point, greater than that, will all be equal to the null class. But if we go to the next type, we can go a little bit further. We get more cardinal numbers. But still, if we start off with a finite number of individuals, the next level up, we only get a finite number of cardinal numbers. Beyond a certain point, they all become the null class. We go to the next level, we can go a bit further, but it's still finite. And so on and so on. So if we start with a finite number of individuals, if we only go up a finite number of types, then we can only guarantee that there's going to be a finite number of cardinal numbers. So this is where the axiom of infinity will start to play a role, which will guarantee the existence of an infinite class somewhere in a high enough type. It's just that to get to certain cardinal numbers, you've got to go high enough, potentially high enough up in the hierarchy of classes to access those cardinal numbers, to get cardinal numbers that are of that size. This is all dealt with in volume 2, and it really does get a little bit complicated, because you've got ascending cardinals, descending cardinals, and things like this, which I'm going to talk about some of the issues in a second. So the cardinal numbers are defined right at the start of volume 2 of Principia Mathematica, and they're defined really in relation to using the concept of similarity. So this relation SM, so alpha SM beta it's a relation between two classes that says that there is a one-to-one correspondence between alpha and beta. So I'm not going to get into how one-to-one correspondence is defined and things like that, but effectively it's if you've got a class alpha and a class beta, then to each member of alpha there is one and exactly one member of beta that corresponds to it, and vice versa. Okay, I know that in modern mathematics there is a word that's often used to describe such a relation or such a function or whatever. I'm not going to use that word because it's anachronistic, and I want to stick to the terminology of Principia Mathematica. As I said in the previous video, imposing modern concepts, modern notation onto Principia Mathematica may cause us to kind of think about things in potentially wrong ways. It might give us the impression that Whitehead and Russell were thinking about things in a particular way when actually they weren't. So I'm careful not to try to avoid using modern notation and modern terminology to refer to the concepts, the ideas, and so on of Principia Mathematica. Okay, so the cardinal number of beta is defined to be is defined in this way. Okay, so what's SM beta, SM primed beta? This is the class of classes which are similar to the class beta. So given a class beta, we can find the class of classes which are similar to beta. And that's what we mean by the cardinal number of beta. But has anybody seen a problem yet? Well, it comes from the typical ambiguity of the symbol SM. So this keeps cropping up, this typical ambiguity, because it's such a big thing. So I'm going to take another example before I come back to this one. So let's take the example of iota. Okay, so we've talked about unit classes. Iota is, so this relation alpha iota x will hold whenever alpha is the unit class of x. Okay. As I've already said, a class, the type of a class is determined by the type of its membership. So if I know what the type of x is, it's of some fixed type, then alpha, which is iota primed x, will be of a predictable type. I know I can infer from the type of x what the type of alpha is going to be. Okay, so that's how it works for some relations, but not all relations work in that way. So for some relations, given a relatum, sorry, you can infer from that what the type of the reference are going to be. But with this SM, that's not the case. Okay, so if I write, for example, SM well, I've already written it, haven't I? This SM right arrow primed beta, I can't infer from this what the object that is being referred to here will be of a particular type, but I can't infer just from the symbol alone what the type of that object is going to be. Unlike in the case of the unit class, iota primed x, I can infer from the type of x what the type of iota primed x is going to be. In this case, with the SM right arrow primed beta, given the type of beta, I can't infer from this what the type of SM right arrow primed beta is going to be. In other words, I can't infer what the type of the cardinal number is that this is representing. There are ways around this, but this is something that you've kind of got to bear in mind. Again, it comes down to this typical ambiguity of different symbols. So this is something that you can compare. You can find one-to-one correspondences between classes of different types. Okay, so SM, the relation SM, doesn't demand that alpha and beta be classes of the same type. They can be classes of different types. But this brings with it the problem that when I want to talk about the cardinal number of beta, I've got to be a little bit more careful, and this is acknowledged. This was something that concerned me. When I first read through chapter 73 in volume 1, when I came across this SM relation, this similarity relation, I was kind of relieved to find that alpha and beta didn't have to be of the same type. But then, actually, I kind of forgot about it, and then I moved on to volume 2, and just as I started reading volume 2, it kind of hit me that there was seemed to be something quite a little bit off about it, about defining cardinal numbers in this particular way. It is addressed, but it's something that you've kind of got to be aware of. Also, if you are working through Principia Mathematica, if you're working through volume 1, part 2 can be quite difficult to get through. There's a lot of new concepts being introduced, and it doesn't really have the flow that maybe part 1 had. So, section C goes through one-to-one relations, many-to-one relations, similarities. Section D goes through selections. Section E goes through ancestral relations. And these don't seem to follow on from each other quite so well, but they are necessary for they're kind of building the foundation for when you get onto volume 2. If you've got to the end of section C of part 2 and you're keen to get on to cardinal numbers and cardinal arithmetic and things like that, feel free to move on to volume 2 at that point. You will need to come back at some point to volume 1 to read section D and section E and things like that. But you are in a position actually to move on to volume 2 once you've got to the end of section C of part 1 and start working your way through volume 2. Because sections D and E are quite difficult to get through in many respects. The point of them is kind of obscured. They're necessary, but they're not used until a bit later on in volume 2. Okay, so what else was I gonna talk about? What got in my notes? So I think I'm gonna have to do another video. This one's starting to go on a little bit. I'll tell you what I'm gonna do before I go. I'm gonna give a bit of an indication about how some of the cardinal arithmetic might actually work. So addition of 2 cardinal numbers, for example. So this is going on to volume 2. So I think it's chapter 110. Yeah, chapter 110. So we've got the arithmetical sum of 2 classes and 2 cardinals. So we start out with this with the arithmetical class sum, as it's called. So this is not the sum of two cardinal numbers. I'm just going to talk about this because I feel like it, really. So we've got alpha plus beta. So alpha and beta are classes. And they're not necessarily classes of the same type. But we can define alpha plus beta, and this is not cardinal addition. This is class arithmetical class sum. This is defined to be down arrow logical product beta double primed iota double prime union. You got to get this right. So lambda logical product alpha down arrow double primed iota double primed beta. So this is a definition. So this looks really mean initially, but this is a very clever way of I particularly like this definition because it takes two classes of different types and it forms a new class of a particular type. So the type of the new class is related to the types of the two original classes that you started with. So let's have a look at this symbol. So down arrow in logical product double primed iota double primed alpha. So okay, what is iota double primed alpha? This is the class of terms alpha. In fact, no, I won't use alpha. I'll just use x. X such that x iota alpha holds. Sorry, x iota y holds for some y in alpha. So that means that x must be of the form iota primed y. So this is the class of terms, class of iota primed y, such that y is a member of alpha. Okay, so this is iota double primed alpha is the class of iota primed y, such that y is a member of alpha. So this class here, this down arrow lambda logical product beta double primed iota double primed alpha, if you go through and figure out what this is going to be, a class of relations. In particular, it's going to be a class of relations of the form iota primed y down arrow lambda beta such that y is a member of alpha. Okay, so this relation will hold. Maybe I shouldn't use y there, actually. I'll use z. Holds if and only if x is equal to iota y and z is equal to well, it's going to be the null class. Okay, so I'm not saying that z is a member of the null class here. I'm saying that z is equal to the null class. Notice that lambda, why have the authors decided to write this? Okay, because this is equal to surely the null class. In fact, I'm gonna write that there. This is surely equal to the null class. This is one of the ways that you can kind of fix the type of the null class. So we've been talking about previously in the video this typical ambiguity of symbols like lambda. Well, here we do need to kind of specify the type of lambda. We need to fix it so that it's the same type as beta. We can do that by writing this lambda, the logical product of the classes lambda and beta. That will fix the type of lambda to the same type as beta. So through the notation, we're building in what the type of the lambda is. Okay, so in this class, then, down arrow logical product of lambda, beta, double primed iota, double primed alpha. How many terms are going to be in there? How many relations? There's going to be however many relations, however many terms there are in alpha, effectively. Okay. And then we've got a similar symbol. This again, we're fixing the type here. Down arrow, double primed, iota prime, what was it, beta. And this is going to be the class of relations of the form that I'm writing on the screen now. Iota primed W, where W is a member of beta. So so notice that in both cases, the logical product of lambda and alpha, this is going to be a class of the same type as iota primed y. Actually, I need to write it over here. So I'm going completely off script here. I'm just talking about whatever I feel like talking about. Feel free to turn off if you want to. And the lambda, the logical product of lambda and beta, that is a class of the same type as iota primes w. So therefore, these relations are both relations of the same type. So we've got iota primed y, down arrow, lambda logical product beta. On the one hand, we've got relations of that form, but they're of a particular type. Now, on the other hand, we've got relations of the form lambda logical product alpha, not beta. And down arrow, iota primes w. But these two classes of relations are both of the same type, so we can find their logical sum, which is what's going on here. So we can jam them together. And how many terms are going to be in that new class that we've formed? Well, it's going to be however many terms were in the class alpha, and however many terms were in the class beta, that number of terms combined. In other words, the number of that number of terms plus that number of terms. But importantly, this has come about through two classes of different types. Oh, the sun's getting bright. Two classes of different types. Alpha and beta were classes of different types. We couldn't just add them together by finding their logical sum or something like that. We've had to be a bit more clever about it. So we found this new class, which has a relation to the two original classes, and which contains as many members in the form of these relations as there were in the original two classes, if we were able to kind of combine them. But we're not. We can't, because they're of different types. Okay, so this leads on then to cardinal arithmetic. So if mu and nu are cardinal numbers, then this is, by definition, the class of, is that chi? Class of chi, such that there is an alpha and a beta, and mu is equal to the cardinal. Okay, so maybe I shouldn't have gone on to this because you've got that then. And nu is equal to n naught c prime beta, and chi is similar to alpha plus beta. Okay, so there is a symbol in here, this n naught. This kind of fixes the type of the cardinal numbers. But importantly, what we're looking for effectively are classes chi that are similar to this class that we've just formed, this alpha plus beta. So this was the arithmetical class sum of alpha and beta. this is the cardinal sum, the arithmetical sum of two cardinals. Okay, so maybe I'm not going to talk anymore about that. What I do want to talk about is chapter 65 in volume 1. Because in volume 1, this is where you can start to take these typically ambiguous symbols and start to relate them to each other. So, in fact, let's start with 63. Chapter 63. Definitely going off script here. Okay, so we can define the type of, let's say we've got a class alpha. We can define the type of the members of alpha as follows. So the type sub naught of alpha is equal to alpha logical sum minus alpha. So of course this is kind of a universal class in a way. So if you look back in section C, for example, you'll find that alpha, the logical sum of alpha and minus alpha is equal to the universal class. So a type, effectively, is a universal class of some particular type of class or whatever. So it's not that it's not that types don't exist before chapter 63. It's just that we're establishing a notation to actually refer to particular types and define types in terms of given objects. And this is really important because we don't have a notion of absolute type. We've only got a notion of relative type. So given a particular object, I can't say this object is of this particular type or that particular type. I've got to refer it to the context effectively. And this might have something to do with incomplete symbols and things like that Whitehead and Russell talk about. That incomplete symbols only have meaning in context. They don't have any objective meaning. Classes don't have objective meaning, except in context. Okay, so given a particular object, we can talk about the type of this object. We can talk about the type of the classes whose members are objects of this type, and so on and so forth. Okay, so if we've got an object X, then we can talk about the type. Sorry, no, it's not T sub 1, it's T. So there's okay, it can be written as just T primed. Sometimes it's written as T1 primed. I'm going to stick with the T primed. T primed X. So these are descriptive functions. And this is the unit class of X, logical sum minus the unit class of X. Okay, so it might be worth noting that if we have, for example, X as a member of the class alpha, then we effectively get that T sub naught primed alpha is equal to T primed X. Because alpha will be of a type 1 above X. And so will the unit class of X will be of a type 1 above X, and therefore alpha and the unit class of X will be of the same type. But what we can say, though, these different notations allow us to say different things. So I can say, for example, using this notation here, alpha is a subclass, or alpha is contained in this type. X is a member of this type. Okay. If we've got that X is a member of alpha, then I can say that X is a member of T sub naught primed alpha. That's if I know that X is a member of alpha. I can also say that alpha is contained in t primed x. So this allows me to start talking about different types and relating different types to each other. And if alpha in turn is a member of kappa, then alpha will be a member of t naught primed, t primed kappa, for example. X will be, wow. It does start to get a little bit kind of complicated, I guess. In fact, I've not really thought about it. This is why maybe I shouldn't have gone off script so much, but you can start relating different types to each other. And I'm not going to say any more about that, but in chapter 65, what we get is some notation that allows us to take a typically ambiguous symbol and fix its type relative to a particular object. So let's take the example of the null class. Okay, maybe I'll say this then. Alpha. So if alpha is any kind of typically ambiguous class symbol, alpha sub x is defined to be alpha, the logical product of alpha and the type of x. Okay, so that fixes the type of this symbol. And then we've got alpha x, which is alpha and the logical product of the type of x. So this goes up a level. So these are not referring to the same thing. This is effectively alpha x is a class. Oh, no, I didn't want to do that. A class whose members are of the same type as x. And alpha x is a class whose members are of the same type as the type of x. So the type of x are effectively classes whose members are of the type x. So alpha x in brackets is a class whose members are classes whose members are of the same type as x. Okay. And okay, we don't go any further. It doesn't go any further with the notation there. Just give me a second. I need some more space. But so with lambda, we can use this notation. We can talk about lambda sub x and lambda of x to refer to null classes of certain types relative to a particular object x. Okay, and it again, we don't have we've always got to define types in terms of given objects. And the chapter 63 goes into detail about this. So if you've making sure that the definitions are kind of well defined. So for example, if you've got x and y of the same type, then what you would expect, if we've got decent enough definitions, that the type of x is equal to the type of y. If that's not the case, then something's wrong. But what that means then is that we can say things like y is a member of the type of x and x is a member of the type of y. So you've got this equivalence, for example. It's all relative. And this is, in my opinion, something to do with the the aim for maximum generality, as Whitehead and Russell saw it. Okay, fixing absolute types it's kind of it's not as general. I've just realised that some of the stuff that I'm writing is probably going to be blocked off by me being down in the corner down here in the video, but never mind. Okay, hopefully you can figure out what I'm writing, even though you might not necessarily be able to see it. So that's how we can fix the types of classes. What about relations? We can fix the types of relations also. So if R is a typically ambiguous relation symbol, we can fix the so we can write R. Let me get. There's all sorts here, so because there's more scope. So R sub X. This fixes the type of the domain of the relation to terms of the same type as X. This will fix so R X in brackets. That will fix the domain of R to objects of effectively the type above the type of X. You can also fix the domain and converse domain. So if you've got R X Y sub XY, this fixes the domain and converse domain to the types of type of X and the type of Y respectively. R X sub Y, this fixes the type of the domain to the type that's one above the type of X, but fixes the converse domain to the type of Y. Similarly, you've got R X Y. This fixes the domain and converse domain of R to the type that's one above the type of X and the type that's one above the type of Y respectively. And there's various relations between these, but notice that there isn't a notation that fixes just the converse domain of a relation. And this is kind of significant, and there's an explanation for this on page 25 of volume 2. Because it's something to do with the notation descriptive functions. So if we've got R is a relation, then we might have relation symbols are often used in the context of descriptive functions, right? So we might have R primed X. So when used in this context, the type of the object X here in R primed X, that fixes the type of the converse domain of R in a number of cases. So there isn't really, based on what Whitehead and Russell are looking to do with these symbols, these relation symbols, there isn't a need really to have a specific notation that fixes the type of the converse domain usually, although there are, as we see in volume 2, there are exceptions to this, and it gets quite messy, some of the notation. So we've already touched on the cardinal numbers. So Whitehead and Russell define the class of cardinal numbers and things like that in the second volume. There are problems with this because it's the notation itself is not strong enough to determine the type of the converse domain of a particular relation and all sorts of things. So I'll worry about that in another video. So okay, I think I've rambled on enough in this video. I've enjoyed it. I've enjoyed talking about this stuff. I think this is probably how a lot of my videos are going to be henceforth, to be honest with you. It's I've got so many notes and things like that to talk about that I really would like the information that I have, what I've learned and what I know about Principia Mathematica and other things. I really would just like to kind of get the ideas out there, and my notes and everything are just building up so quickly that I can't possibly I haven't got the time to properly write out scripts and make videos and things like that. Really, I'm just going to have to sit down in front of the camera and just start talking most of the time. So, as I said at the beginning of the video, if you've managed to watch the video to this point, very well done. Congratulations. But either the videos will be useful or they won't. If there is anything useful in these videos for you personally, then you maybe just going to have to be patient and actually find what's going to be relevant to you. I honestly didn't expect to be talking about some of this stuff in this particular video. Hopefully you found something useful here. If you do have any questions, then please feel free to ask. In the description to this video, I will leave a link to my Buy Me a Coffee page. As you've seen, I do like coffee. If you would like to buy me a coffee and you are in a position to do so, then that would be very much appreciated. If you are not in a position to buy me a coffee, then please don't worry about it. But it will be very gratefully received if you are in a position to do so. If you do have any ideas about anything that you'd like me to cover, any questions that you've got about Principia Mathematica, please feel free to ask. I'd be very happy to answer any questions that you've got. So I'm going to leave it there for this video. I think I've spoken long enough. So thank you for watching, and I'll see you in the next video.